Hello everyone, welcome to this presentation entitled The Origin of Electromagnetic Radiation. This is the second part of this topic. In the first presentation, we have seen an introduction. We have also seen the basic equations of electromagnetic radiation, and also we presented the fields created by a charge in motion, and we discovered that the electromagnetic radiation is always produced by the accelerated movement of a charge. So in this second part of this topic, we are going to see how oscillatory charges operate, and also we will show how to calculate the radiated energy density and total power emitted by an oscillatory charge. And finally, we will talk a little bit about the momentum of light. Most of the information in this presentation has been obtained from this reference here, the Feynman lectures on physics. So if you want to have more information about this topic, please take a look at this reference. Remembering what we saw in the first part of this presentation, we studied the charge in motion and we calculated the electric field generated by this charge. So we have a total of 3 components for this electric field. 2 of them here are what we can call the near field, and we know that this is a field that is going close to the particle, and if we are a few wavelengths away from the particle, the field is already very small. The amount of energy that we can get at this distance is almost negligible. But we have the third component that we can call the far field, and this is a field that transports energy far away from the particle. So if we are a few wavelengths away from the particle, the only electric field that remains is that corresponding to the radiation, and we have this expression here which is related with this term to the acceleration of the particle, as we have seen previously. So now, in order to evaluate the electric field generated by this radiation when we are far away from the particle, we are going to calculate the acceleration of the particle, in this case when we are situated at a point which is very far away from the particle. So let's say that the particle is at a given instant at this point A, and then we are going to, or the particle is going to move to another point B here. So the movement of the particle, which is this here, can be decomposed in 2 components. One is delta y in the y direction, and the other is delta x in the x direction. We have to consider that the distance is very much greater than these 2 components. So in order to calculate the speed of the particle and also the acceleration, we obtain first the unit position vectors in both positions A and B. Here in the first position A, we have this unit vector, and is going to be equal to the unit vector j in the y direction. And in the case of the other unit vector for the position of the particle at B, then we have this expression here, which is the vector, the position vector corresponding to B divided by the magnitude of this position vector. It's very easy to calculate. So if we consider these conditions here, because r is much greater than delta y, then we can do this approximation. Also here, this is small and this is small compared with r, so we can approximate the distance equal to r. So we have finally this expression here and this other expression here in order to obtain the unit position vector of the particle at B. So now, in order to calculate the speed of the particle, we take the difference of these two vectors and we obtain this value here. So the velocity of the particle can be obtained by this difference in the two vector positions divided by the difference in time. So we get this expression here, which is going to be the speed in this direction, in the x direction, divided by r. If we take again the second derivative, which is the derivative of the speed in time, we finally reach at this expression here, which is the component of the acceleration divided by the distance r in the direction I, in the x direction. So the conclusion here is the following. If we are very far away from the particle and the particle is moving, the only component that is going to be important for us is the component of the acceleration, which is normal to the line of sight. The line of sight is the line that joins the point at which we are calculating the field with the particle. So the component of the acceleration in the y direction is almost zero. So is the component of the acceleration in the direction of the line of sight is almost negligible, while we have to consider only the component of the acceleration normal to the line of sight. So knowing this, if we want to calculate the electric field corresponding to the radiation at a given point P here and at a given instant T, we have to consider the position of the particle, as we know, at the time instant T minus R over C, which is the retarded position. And then what we have to obtain is the component of the acceleration in the normal direction of the line of sight. This component is very easy to obtain knowing the value of the acceleration vector. The normal component is going to be equal to the magnitude of the acceleration times the sine of the angle theta. The angle theta is the angle of the acceleration of the particle with the line of sight. So from this expression here, which is the general expression, we can obtain this expression here in which the acceleration is this value here. So we have to consider the retarded acceleration and multiply it by the sine of the angle theta and divide by the distance r, which is the distance of the particle at the retarded time when the radiation was emitted from the particle. And now we are ready to study the case of an oscillatory charge in which the charge is describing a simple harmonic motion as shown here. And this could be the case of a charge accelerated by thermal energy. So in this case, we want again to obtain the field at a given point P and at a given instant T. So in the case of a simple harmonic motion is very easy to analyze. We have this expression here for the movement of the particle following a cosine in time. Then we can obtain the speed of the particle by taking the derivative with respect to the time. So we get this expression here. And if we take again the derivative, so the second derivative of the position with respect to the time twice, then we can get this final expression here for the acceleration. So using the equation that we have just seen in the previous slide, then we can substitute the value of the acceleration, and then we finally get this expression here, in which we see that we have considered not the same instant at a point P at which we want to calculate the radiation, but the time instant corresponding to the retarded time, T minus R over C. So this is very important in the case of electromagnetic radiation. You have to consider this retarded time. And this is also the reason why this radiation is going to behave like a wave traveling in the space, because this equation here corresponds to the equation of a wave, as we are going to see right now in the next slide. So summing up, when we have a particle describing a harmonic motion like this with an acceleration on this direction, and we want to calculate the field radiated at a given point P and a given instant T, which has a line of sight forming an angle theta from it, then the field is going to be always normal to the line of sight, as we can see here, and this is the value that we will obtain for the electric field. And this expression corresponds to the expression of a wave, because if we fixed the value of the distance, for example r equal to r1, then we remain at a given position and we evaluate the value of the electric field in time, then we are going to have an evolution like this, in which we have a given amplitude and a period which corresponds to this value here, 2 pi over omega, where omega is one of the important parameters, as we have seen, of the electromagnetic radiation, and is called the angular frequency, which is the rate of change of phase with time. And also, if we fix the time instant and we analyze for a given time instant t1 how the radiation is changing with the distance, then we will obtain an evolution like this. Here is the radiation, the amplitude of the electric field represented against the distance. And then we will see also a cosinusoidal evolution, in which we have another important parameter here, which is lambda, the wavelength, which is equal to 2 pi over k, where k has the value omega over the speed of light and is known as the wave number, which is the rate of change of phase with distance. Now we can understand the operation of a very simple radiator, which is the dipole radiator. The dipole radiator is made up with two wires like this, at which we are connecting a voltage source generating a voltage that follows a cosinusoidal evolution in time. So when the voltage is positive like this, the electrons of the wires in the dipole radiator are going in this direction. So in both wires, the electrons are going down. And when we applied negative voltage with the voltage source, then the electrons are going to move in these other directions here. So in both wires the electrons are going up, so they are going to do a simple harmonic motion following the expression of the acceleration that we have seen before. So with this we can generate electromagnetic radiation out into the space. To test the radiation emitted by the dipole, we can use another dipole as a sensor in order to measure the radiation received. So with another dipole connected to an amplifier and then to a voltmeter, we made our sensor of electromagnetic radiation. So if we place our sensor in this position here because the angle is maximum, then we have our dipole radiator here. The acceleration goes in this way, so the electromagnetic field that we are going to get is also in the normal direction. So because the angle is 90 degrees, then we are going to get the maximum value of the radiation. If we place our sensor at the same distance but with an angle of 45 degrees, then we will get a lower value of the radiation because only the normal component of the acceleration is going to generate field, as we know. And if we place the sensor at an angle equal to 0 degrees, then we are only, from this line of sight, we are only seeing the electrons moving closer and farther to us, so there is no radiation in this direction. So here our sensor is going to give us 0 voltage. So this is the reason why the radiation pattern of a dipole is as shown here. It is like a donut. We have 0 radiation in the same direction of the dipole, and the maximum radiation is in the normal direction of the dipole. Now we are going to calculate the energy density radiated from a particle which is describing a simple harmonic motion. For this we start with the energy density, which is 1 over mu 0 times the electric field cross product magnetic field. Now we are considering only the electromagnetic radiation. So using the expression for the magnetic field that we have seen in previous slides, then we can obtain this expression for the energy density, the radiated energy density, which is the speed of light times the permittivity of free space times the electric field squared. But this electric field is changing in time following a sinusoidal also evolution in time. So we are interested now in the average value of the energy density that we can obtain with this expression here. So what we need is to calculate the average value of the electric field squared. And the electric field square, we can obtain it from the expressions that we have seen before. So we will obtain this expression here. So from it we can calculate the average value of the energy density using the equation that we have seen here. So because the average value of a cosinusoidal waveform squared is 1 over 2, then finally we get this expression here. So this is the energy density that we are going to have from the radiation of a particle moving following a simple harmonic motion. Now we want to calculate the total energy emitted by this particle. So for this we have to do the integral of the energy density going through a sphere surrounding the particle. So we perform this integral here. This is simple mathematics, so we can consider this differential area here, which can be obtained with this expression, and then by integrating from an angle theta 0 to an angle theta equal to pi, then we can obtain the total energy emitted by the particle. So we finally obtain this expression here. And because the acceleration in a simple harmonic motion is related to the frequency, with this expression that we have also seen in previous slides, then we finally obtain this expression here. So the total power is following this expression, in which most of them are constant, is proportional to the frequency to the fourth exponent. So this is very important. So the total energy, the total power is increasing very much with the frequency of the radiation, and also is proportional to the maximum displacement of the particle squared. So we can see finally that both the energy density and the total power are proportional to the frequency of the electromagnetic radiation raised to the fourth exponent. This is very important, so we can see that the higher the frequency, the higher the energy density that is being transported by the electromagnetic radiation. And this is also related, for example, with the fact that we see the sky so blue, because the particles in the sky are vibrating as a consequence of the radiation emitted by the sun, and the highest frequencies are the frequencies in the blue radiation. So this is the reason why we see the blue radiation, because most of the energy is radiated back into the blue part of the spectrum. So now we can understand better the behavior of our dipole radiator. Here the electrons are going to describe simple harmonic motion, and therefore they are going to emit radiation. The total power emitted in the form of radiation has been calculated before, and it in the ideal case is going to be equal to the power consumed from the voltage source by our dipole radiator, so that our dipole radiator can be represented as an equivalent resistance, and the power consumed by this resistance is equal to the power radiated by the dipole. At this point, we can ask ourselves what is the origin of this power, because at the end we need to fulfill the law of the conservation of energy. So what is happening to the particle is that when it is moving with a given acceleration, it is going to experiment a recoil force against the movement of the particle, in such a way that this force times the distance that the particle has described during a given time interval has to be equal to the radiated power times the time interval. So in this sense, this recoil force is like a friction force against the movement of the particle. So this force tries to decelerate and stop the movement of the particle. In the case of a charge moving with a constant speed, then the acceleration is zero, and therefore the electromagnetic radiation is going to be zero, as we know. But this happens only if the particle moves at a constant speed and following a straight line, because we know that even if the particle is moving at constant speed, but the trajectory is not a straight line, is a curve, then the particle is going to have an acceleration due to the curvature of the trajectory. So finally, at this point, we see that we have almost talk about the electric field of the electromagnetic radiation. So we can ask ourselves, what about the magnetic field, the effect of the magnetic field? From the Lorentz law, we know that the magnetic field only acts on charges that are moving with a given velocity v, following this expression here. So what is happening with the electromagnetic radiation when it interacts with the matter is that the electrons are going to oscillate, as we have seen, due to the effect of the electric field. and therefore then the electrons are going to move, and this movement is going to interact with the magnetic field. So following this expression here, we can see that the force that is going to be exerted on the electron is following this expression here, q times the velocity cross product the magnetic field. So there is a force in the same direction as the movement of the electromagnetic radiation. So the electromagnetic radiation is generating at the end a pressure on the matter, and this is called the radiation pressure. So we can now see that light carries not only energy but also momentum. And the reverse action is also true. When the light is emitted from a source, there is a recoil effect on the source. So here, when the particle is emitting the electromagnetic radiation, there is a force against the particle again. For example, when the light is reflected normally from a mirror, then the recoil force is double because we have a force when the electromagnetic radiation is arriving to the surface of the mirror, and then we have another force when the electromagnetic radiation is being emitted back, reflected from the mirror. This is an effect that has been already taken advantage of in the development of spacecrafts known as solar sails. Well, this concludes this presentation today. I hope this information is useful for you. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.